Thank you so much for inviting me to give a talk and to the organizers for putting on such an amazing conference. And I'm also happy to see so many young people who are interested in combinatorics and so on. So what I want to do is I want to talk about a q-deformation of the Q-Tsetlin library. And this is a joint work with Arvind Ayyer, Sarah Brauner, and Gier. And before I start talking about the Q-Tsetlin library, I want to tell you a little bit about the collaboration. So we started working together at IPAM. I think in 2024, there was a program at IPAM. And Sarah Brauner actually gave a talk about Hecke algebras and so on. And then Arvind Ayyer was there and Gier was also there. And we were talking about how one could make a Markov chain out of that. And that's how the whole collaboration started. And we are all on different sort of continents, like Arvind is in India, Sarah is on the East Coast. Okay, that's the same continent, but Gier is in Australia. So it's actually very hard to find a time to all meet, even on Zoom. So often we just have to meet in subsets. And then we were able to meet again at ISOM, and that's where we sort of finished the whole thing. So I'm very thankful to the Math Institutes where we were able to do the research. Okay, so I want to tell you about the q-deformation of the Q-Tsetlin library. And so I will start with telling you about what the Q-Tsetlin library is. And for that, we are going to look at a picture of my bookshelf. So that is actually part of a bookshelf at home. And you can see like a couple of books, right? So Fermat's Last Theorem, the code book, A Beautiful Mind, and then you like the one about the zebras and the ulcers. So what is a Q-Tsetlin library? But it's sort of like, it's just a bookshelf with, let's say, n books on it. And what you do is you pick a book at random, but with some probability, and you take it out, you read it, and the librarian is lazy, so the librarian just puts it at the beginning of the book stack, right? So you take it out and you put it at the beginning of the book stack. So I guess now we should vote. What is your favorite book? The Algebra? Yeah, okay. Who would like the Fermat's Last Theorem? No? Okay. The code book? Okay, couple of people. The Beautiful Mind? Okay. Should I go through all of them? Okay, so in any case, how many people like the zebras and the ulcers? Oh, okay, so that's definitely the okay, so we would pick that book because most of us like that book apparently, right? And we would take it out and we put it at the beginning of the stack. So that's sort of like the Markov chain. Okay, so and in math, instead of calling it Fermat's Last Theorem and so on, we call the books 1 up to n. So we have finitely many books. And our state space of our Markov chain is all permutations of the books, because the books could be in any arrangements, right? So that's n factorial ways of putting them on the bookshelf. And then, as I just said, so we give each book a probability. So the zebra book would have the highest probability in this room, and Fermat's Last Theorem would be pretty unpopular. And then what you do is you run this process over and over, right? And you move the things to the front. And if you do it over and over and over, the most favorite books will end up at the front of the stack. And you can also think of it like your shirts, right? You always wear your favorite shirt, you wear it, you wash it, and you put it at the top of your stack. You don't put it at the bottom. And then it's always very hard to find your unpopular shirts because they're down, very far down in your stack. So that's what this thing is modeling. Okay, yeah, so the popular books will end up at the front. And so what people are interested in is, if you run this process over and over and over, you would like to know what is the distribution of the books. So that's also called the stationary distribution. And another thing that people would like to know is, how quickly does it get there? Like how many iterations do you have to do to actually get close to the stationary distribution? Okay, so here's another sort of example. This is our state space. So let's suppose we have 3 books. Then we have 6 permutations. So I've drawn them here. And I hope the colors are coming out. But so let's suppose we take this 1, 1, 2, 3, right? So that's the identity permutation. Then we could either pick book 1 and take it out and put it at the front of the stack. So that's this little arrow 1, right? Because it goes back to itself. Or we could pick book 2, and then we would get to 2, 1, 3. Or we can pick book 3, and then book 3 would be at the front, so we go here. So this diagram here sort of is a visualization of the chain. So basically you're taking a walk on this graph. And then a blue edge has these edges would then have different probabilities. Okay, so here's again our state space, and I'm now ordering my permutations in a certain way, because now I'm going to sort of encode the probabilities in a matrix, right? So if I order my permutations this way, then, well, we saw that down here, if we pick book 1, right, we would pick it with probability 1, then we would get an x1 here. We go from 1, 2, 3 to 1, 2, 3. If we pick book 2, we would go to this particular state, and we would do that with a probability x2. So 2, 1, 3 is in the 3rd position. So that's why in the 3rd place in my row here, I have an x2. And if we pick book 3, we would get here, which is the second to last permutation. So that's why we have an x3 in this spot. And then you can fill out the whole matrix, right? So you get this matrix, and this matrix encodes the entire Markov chain. So it's also called the transition matrix. And the stationary distribution, so the distribution that you would like to get after you run it over and over and over, mathematically speaking, is really the eigenvector of eigenvalue 1, because if it's that eigenvector, then if you do t again, it just stays where it is, right? So that's the one that you get when it's sort of stabilized. Okay, and so in principle, you can now do Sage math, right? You put this particular matrix into Sage math, you ask for the eigenvector, and out comes this, and it looks relatively nice, right? So it has like products of the x's in the numerator and sums of x's in the denominator. And so what I want to do in the first part of my talk is tell you how you can actually derive this with some sort of modern methods. And those are also the methods that we then use for the q-deformation. Okay, and before I do that, let's reformulate the problem slightly. So instead of writing it as a matrix, I'm now going to write it as an operator. Okay, so Si is just the operator that interchanges I and I plus 1, the simple transposition. So if I look at this operator, so I'm acting, my vectors are on the left, right? So I would act with Si minus 1 first. So that interchanges I and I minus 1. And then I do Si minus 2, so that basically moves that book to the front, right? If I do Si minus 1, Si minus 2 all the way to S1, then I've moved the book in position I to the front. And that's sort of what we do. We pick a book and we move it to the front. And then the sky is the probability that we assign to it. And the probability is basically the one that ends up at the front. So if I write it, we have taken out the pi I, we moved it to the front, and then the probability is with respect to the thing that is at the front at the end of the process. Okay, and so Hendricks in 1972 gave the stationary distribution, and indeed, it's not just a fluke for n3, it is indeed a very nice formula. Right, so it's a product of x's in the top and then these sums in the bottom. Oh, and I should also say, because that will come up later, the x's sum up to 1 because they're probability. So I could also write this as 1 minus the remaining x's. And this is actually what comes up in the formula that I will give. Okay, so now what I want to do is give you sort of an alternative derivation of this using what's called geometric finite semigroup theory. And so this was first developed by Diaconis and Brown for certain hyperplane arrangements, and then developed further by other authors. And I will tell you about the method that I developed with John Rawls, where we use semigroup theory. Okay, so how does semigroup theory come in? So that's what I want to explain now. So first of all, what is a semigroup? It's just it's basically a group where you don't have an inverse and not necessarily an identity. So you have a product and it has to be associative. Okay, and if we look at the set of all subsets of the numbers from 1 up to n, and we take multiplication as union, right, that would be a semigroup because we can union things and that's associative. Okay, so that will be my semigroup. And in fact, it is what it's called a left regular band. So what is a left regular band? It's a specific semigroup that satisfies these identities, namely UVU has to be UV and UU has to be U. So let's think about it for this particular semigroup, right? If I take a subset and I union it with itself, it's still the same subset. So we definitely have UU is U. And also, if you add a subset, you union it with something else, and then you union it again with itself, it's again just the union of the two other subsets. So this particular semigroup that I gave you here is indeed a left regular band. And now I'm going to write down a Cayley graph for this. So for the Cayley graph, I have to have generators of my semigroup. So the generators in this case are just the singleton subsets, right? Just the 1, a 2, or 3, n is 3 in this example. And this 1 here is basically just the empty set. So if you take the empty set, you union with 1, you get here. If you union with 2, you get here, and so on. If you take the subset 1, you union it with itself, you stay where you are. If you take 1 and you union it with 3, you get to this one, but you could have also gotten there by first union with 3 and then union with 1. So it looks like a cube, right? Okay, so that's the right Cayley graph of this particular Markov, of this particular semigroup. And then, so what does it have to do with the Q-Tsetlin library? Well, there is something called the Karnofsky-Rhodes expansion. And let me explain it on this picture. So basically, we will now distinguish edges that sort of go down where you cannot go back up, right? So we have these edges. Once I union with 1, I can never get rid of the 1. But then there are also edges where you just cycle. So these are not transition edges. And then once I union with 3, again, I can never get rid of the 3. So these blue edges are called transition edges. And for this Karnofsky-Rhodes expansion, you would like to distinguish in which order you took the transition edges to get to a particular point. So for example, this 1, 3, we will distinguish between getting there by first doing a 1 and then a 3 versus a 3 and then a 1. Okay, so once we do that, we get to this picture. So we've now sort of expanded the transition edges, and now you can sort of see the Q-Tsetlin library coming up, because now here at the bottom you can see our 6 permutations, right? Because now we distinguished, so the 1, 3, for example, right? The 1, 3 is here, but the 3, 1 is over here. And this is the picture, and this thing at the bottom is also called the minimal ideal. That's the one where you get to and then you can't get out of it, right? Once you are here and you now union with something else, you stay where you are. Okay, so yeah, the minimal ideal are these permutations, and our Markov chain will always be something on that minimal ideal, will be something, some walk on the minimal ideal. And so how did we get there? Well, we did write Cayley graph, but to actually get the Markov chain we are interested in, we have to do left multiplication. So you have to keep your left and right straight in this business. Okay, because why is that? Well, let's take again our 1, 2, 3, right? If I pick book 3 and I move it to the front, well, I would first have to multiply by the 3 on the left. Right, so if I take this and then I first multiply by 3 on the left, and then I do my 1, 2, and then another 3, but the 3 would just cycle, then I get to 3, 1, 2, which is precisely the one where we moved the 3 and we moved it to the front. Okay, yeah, so left and right is important in this business. Okay, and so now I want to show you how we can now rederive the Hendrix result, the stationary distribution. And to do that, we are going to look at the paths that go from up here all the way down. And so intuitively speaking, right, when you're up here, you know nothing. And once you're down in the minimal ideal, nothing happens anymore. So you're sort of in stationarity. So what you would like to know is what's the probability of getting to a particular thing in the minimal ideal, okay? And we do that by taking these paths to the minimal ideal, right? So a particular path to go, let's say, to 1, 3, 2 would be we take 1, 3, and then 2. But there are more paths that you could take, namely there are all these loops. So I could do a 1, and then I could cycle there and do a 1, and then I could do a 3, and then I cycle there, and so on. So all the paths to a particular permutation would be given by this, where pi 1 star just denotes you can do it an arbitrary number of times. Okay, and then, yeah, so this is basic, these ideas are basically already present in this paper by Brauner and Ayyer in 1998. So to get the stationary distribution, you look at the probability, you compute the probability of starting at the top and reaching a particular element. And then, so this particular picture is for a left regular band. So these are very special semigroups. So with John Rhodes, we actually extended this to the finite Markov chains for any semigroups, not just left regular bands. And then instead of having to do the Karnofsky-Rhodes expansion, you also have to do a McCammond expansion. But I'm not going to talk about this in this talk. Okay, so now let's compute the probability of getting to a particular permutation. So what do these stars do, right? Well, the star means either I don't take the step, or I take it once, but that would be with if there's a loop, let's say 1, that would be with probability x1. If I take it twice, it would be x1 squared, and so on and so on. I have to sum them all up, but that's really just a geometric series, right? Because it would be 1 plus x1 plus x2, x1 squared, blah, blah, blah. And we teach our calculus students that this is just 1 over 1 minus xa, okay? So that's, I hope you can already see where these factors in the stationary distribution are coming from. And then if I have, here I also, remember I can have a pi 1 or pi 2 star. Well, if you do that, then the probabilities just add up and I get 1 over 1 minus the sum of the two and so on. And now you can see how you actually get the stationary distribution, right? The things in the numerator are precisely these transition edges where we go down, and then the things in the denominator are precisely these things that come from the loops, which you got from the geometric series. Any questions so far? Okay. Yeah, so this is just a re-derivation of Hendrik's result, and Hendrik's derived it using different methods. So he had some recursion relations where he had probabilities coming in and out, and then he solved these recursions. That's how he proved this result. Okay, so now we talked about the stationary distribution. There are other things that you can ask about such a Markov chain. Namely, you can ask about the eigenvalues of this matrix. And in this case, they're actually also very nice. And in 1991, Rutherford actually computed the eigenvalues of the Q-Tsetlin library. And they're given by nice combinatorial objects. Namely, for every subset of the set from 1 up to n, you get an eigenvalue where then you just add up the x's with respect to that subset, and they occur with a certain multiplicity, and the multiplicity is precisely the number of derangements. Okay. And then I told you that other things people are interested in are mixing times, and for the Q-Tsetlin library, Diaconis in 1988 computed the mixing time, and it's of order nlogn, where n is the number of books. And I should also say, so this is when all the weights are equal, so when all the xi are 1 over n. Okay, so now I've told you everything that's sort of known, or most of the things that are known about the Q-Tsetlin library. So now the next thing I want to do is tell you about q-deformations of this. Yeah, so one thing, as a spoiler alert, we will have to use some geometry to actually get the stationary distribution. And another spoiler alert is we actually get a better mixing time than the nlogn that you have for the usual Q-Tsetlin library. Okay, so how do we q-deform it? So recall that I wrote our sort of operator this way, where we took the sum over these products of these SI. But the SI we could now replace by operators in the Hecke algebra. And the Hecke algebra is sort of like a q-deformation of the symmetric group, right? So the generators of the Hecke algebra are Ti. I'm going to denote them by Ti. They also commute when they're far apart. They also satisfy the break relations, but they satisfy a more complicated quadratic relation. So Si squared is 1, but for the Ti's you get this relation, which involves the Q. So that's where the Q deformation is coming in. Okay, and then I told you, so Sarah Brauner gave a talk at IPAM where she actually talked about this particular operator here without probabilities, but you can see that this operator is precisely this operator without these probabilities, right? So that's how sort of the project started. What we were interested in is, well, can we also put in probabilities and then compute stationary distributions and eigenvalues and mixing times and so on. Okay, and so what I want to do in this talk is tell you about 3 different q-deformations of the Q-Tsetlin library. So we will take this particular operator, but we have to act on something. And so one is we are going to act with the Hecke algebra on permutations. So that will be the first one. We can actually also act on words, so where we have repeated entries. And then the last one, and this will actually be the one that will be really important for the proof, is the one where we actually have an action of the Hecke algebra on flags. So that might look a little bit weird right now, but it turns out that this is actually still a left regular band. So we can use a lot of the machinery we've used before, whereas currently we don't know how to formulate these two as a nice semigroup. I mean, in principle, you can still write it down as a semigroup, but then it will be much harder to actually derive the stationary distribution. We are actually going to this one, and then we get the others by lumping. Yeah, so that's what I just said. So this is the one on flags is a left regular band, so we can actually do stuff, and the other ones we get by lumping. Yes.
Is there a interpretation of the Markov chain, like using the books in the library? See for number one.
Yeah, yes, I think, yeah. So basically, either you move the book or you leave it where it is. So on the next slide, I will, yes. So yeah, either you move it or you don't, and the probability when you don't, that depends on 1 over q.
Okay, thanks.
Yeah, so that's on the, not this slide, but the one after. So yeah. Okay, so what I will do for the rest of the talk is I will give you the definition of these. I will tell you about the stationary distribution, eigenvalues and multiplicities, and then also mixing time. Okay, so let's begin by defining the first one, the one on permutations. And this is the action of the Hecke algebra on permutations. So if I have a permutation pi and I act with ti, well, if pi I plus 1 is smaller than pi I, we will flip it, and there's a factor of q. And in the other case, we flip it or we don't flip it, but either with a q or 1 over q. So if you divide this whole equation by 1 over q, then you can see here we would just get pi as I. So in that case, you would just flip as before. Here you would get 1 over q pi as I, and then 1 minus 1 over q pi. So I think this answers your question. So, right, so either you flip or you don't. So in this case, you either flip or you don't flip with probability 1 over q. Yeah, so I think, yeah, you can still interpret it this way. And then, yeah, so our definition is now basically exactly the same as before, where the s's are replaced by the t's. And, well, so the hard part was to figure out what the probabilities actually are. And you can't just put x's in here. So you actually have to scale them with q's. And we will see later that this actually comes from the fact when we look at the action on the flags, the sizes of certain flags, of certain equivalence classes of flags, that's precisely, they precisely have sizes like this. So we sort of scale by the 1 over q and minus pi. Okay, so here's sort of a summary of what has happened so far, right? I first told you about the Q-Tsetlin library. Well, if we set all x's to 1 over n, we get a random to top operator. Now I've told you about the q-Tsetlin library. If we set q as 1, you actually get the usual Q-Tsetlin library. Perhaps I can go back, right? If q is 1, then, well, it's always, you're always acting with si, so nothing. It's the same as the Q-Tsetlin library, right? And then to actually get to a q random to top, you have to set these x's to some scaled version, some q-deformation of 1 over n, where n sub q is a q-deformation of n. Okay, and so when we were at IPAM, well, we put this on the computer, you get, again, matrices like this, right? But now they have q's. And then you would like, again, to know what is the stationary distribution. So you ask Sage, or actually, I think Arvind did it with Mathematica. And then you see that they're, again, sort of nice formulas. So then we got hopeful that we could do something. And then we also looked at the eigenvalues. The eigenvalues also still look nice, right? They're still sort of sums of the x's, but now there are powers of q in there. yeah, and then so we were interested in finding the general formula. And now I'm just going to tell you what they are, and then I will tell you how we actually prove them. So it's not super important that you understand the full sort of formula, but what I would like you to see is that it looks similar to the Q-Tsetlin library. Namely, so it might even be too small to read, but there again, like these factors in the denominator, 1 minus something, there are q's in there, and these kappas, they are sums of x's, right? So it's a q-deformation of these geometric series that we saw before, the 1 over 1 minus function of x's, that's now this 1 minus q, and then these kappas. And then the numerator, where we just had the product of the x's, is now also q-deformed, because either we switch or we don't switch. So that has also become slightly more complicated, but I hope you can see that the structure is sort of still the same. So it would be hard to guess the formula, but once you sort of know how to derive it, you can see that it follows sort of a similar thing. Okay, and so we also got the eigenvalues. So again, before we looked at all subsets of n, and for every subset we had an eigenvalue. That's still the case, but now they are slightly q-deformed, right? So there are also powers of q in there, but the multiplicities are still the derangement numbers as before. Okay, so now I want to briefly, just on one slide, tell you about the Q-Tsetlin library on words. So instead of acting on permutations, we are now going to act on words, where the content is specified. Yes?
So I just ask with the eigenvalues, is there a reason we should expect the eigenvalues are all real?
No, in principle not, no. I mean, it's surprising, yeah.
Okay, thanks.
Yeah. Yeah, so okay, for the Q-Tsetlin library on words, so we fix the number of ones, the number of twos, and so on. And then we again have an action of the Hecke algebra on words. So remember before we were either flipping the pi I and pi I plus 1. So we do the same here. We flip wi and wi plus 1. When now in this case, wi plus 1 is less or equal to wi, right? Because we can now have repeated letters, or we either flip or we don't flip. So when they're all distinct, it's again exactly the same as for permutations. And the probabilities again are slightly more complicated. So it took us actually like a whole weekend to work that out at ISOM. But once you get all the conventions right, this is sort of the right way to q-deform our x's. And then with these particular probabilities, we get again a nice stationary distribution and nice eigenvalues and so on. And our walk is given by this particular operator on words. So I'm sparing you the formula for the stationary distribution, but it looks similar to the one that I just showed you. Okay. So we found these on the computer and so on, but we weren't actually able to prove them using left regular bands and so on. So we actually needed to appeal to another way of describing things, namely another action, and that's what I want to tell you about now. Namely, we had to look at the action of the Hecke algebra on flags. Okay, and we are going to look at flags over finite fields. Okay, so we have a finite field with q elements. And we are looking at the action of GL and FQ, and B for us is the upper triangular matrices. And we are looking at complete flags. So a flag would be a sequence of subsets. such that the dimension of the ith one is equal to I. Okay, but so it's important that we are working over finite fields because that's how the Q is actually coming in. Okay, and so if EI is the vector in direction I, then this would be like a standard flag. So how do we get a left regular band from this? Well, let's look at sort of partial flags. And by partial, I really mean, so the first I subsets are of dimension 1, 2, 3, and so on up to I. But you don't go all the way to FQ to the N. Okay, so you stop at some point. So if you think about it in terms of the letters, right, how did we build up our Q-Tsetlin library? Well, we first added a 1 and then a 2 and then a 3. So that's sort of partial words or partial permutations, right? So that's why here we have to look at partial flags. And then what is the multiplication? Well, think about the multiplication when we took the word. That's basically just concatenation. And then you remove repeated letters. That's how you can think of it in terms of just words. Here, if we multiply two partial flags, well, we take the first one, and then we sort of add the subspaces of the second one to the last one. Okay, but then it could happen that you get repeated things, and so this hat here means remove repeated subspaces. And this in turn, this in fact is a left regular band. Okay, so and that's what we are going to use because for our proofs, I mean, to prove the stationary distribution, we really need some nice description in terms of semigroups. So here are some facts about these flags. So they are n sub q lines, and the number of flags is n sub q factorial. So let's do an example. Let's take n is 2, q is 2. Okay, so then the claim is that we have 3 lines. So they are given by E1, E2, or E1 plus E2, right? So you can't have bigger multiplicities because we are working in FQ, right? So you only get 0 or 1 as multiplicities. And then what are our flags? Well, here are the 3 flags, right? We can add one of the 3 lines. So that's sort of here. Or and then we already after that have the full space because n is 2. And what I want to do is sort of group flags together. So and this is also what how these q powers and so on come in and how we assigned our probabilities. So the probabilities we want to assign to these lines is basically by looking at the support of the line. So this one has support 1 because we have E1. This is support 2. This is support 1, 2. And we are looking at the minimal element in the support, and that is sort of the probability we want to assign. And therefore, we are sort of grouping things by the minimal thing in the support. So therefore, I want to sort of group these 2 things together. And if I write this in terms of a matrix where the first column sort of gives me the first subset, and then the next column gives me sort of the extra vector in the next subset, then we could write these together as one alpha, where alpha is either 0 or 1, but it's 0 for this flag and 1 for this flag, because here we have E1 plus E2. And we would write this in terms of this matrix. And then this flag, well, this has support 2, so we would write it as this. And you can already see that we can assign permutations to this, right? This would correspond to the identity permutation, and this to the permutation that flips 1 and 2. Okay, so basically what I've just explained means we can sort of group flags together into equivalence classes. And here's a slightly bigger example, right? So all of these matrices that would correspond to different flags, I want to assign to the permutation 1, 2, 3. And this one I would assign to the permutation 2, 1, 3, right? It basically looks at where the ones are, and so on and so on. And you can already see that these equivalence classes have different sizes, right? Because there are different numbers of free parameters. Like this one here has no free parameter, and this one has 3 free parameters. So you get different sizes of these classes. Okay, and there's in fact an action of the Hecke algebra on these flags, which we found in a paper by Halvorsen and Graham from 1999. And it can already be found in a paper by Iwahori, but Halvorsen Graham is very nice to read, so I recommend that paper. Okay, so what is this action? If Ti acts on a flag, then what you do is you take your ith subspace and you replace it by a different subspace that has to be different from the original. And you sum over all such subspaces. And that is the action of the Hecke algebra. I mean, that it doesn't look obvious. So, I mean, you have to check things, but that's what they worked out. And here's like an example, just to sort of convince you. Let's take the flag, the last one, which corresponded to 3, 2, 1, right? And let's act with T1 on it. So what do we have to do? We have to take our first subspace and we replace it with every other subspace that is contained in the second subspace. So in this case, if you look at the first 2 columns, right, the subspace would be E2, E3. And so the one that is not equal to the first one, right? Because we want this condition would be you take 0, 1, 0, or you can also take something here and something here, where T is non-zero. So that would be sort of in matrix notation, this formula. And that you can write as this, but this is basically, since we are summing over all alpha, this is basically the full equivalence class 2, 3, 1. And that would be the action of the Hecke algebra when we do the flip. Okay, and here's another example where we do both, we do the flip and we don't do the flip. So if we act with T2 on this particular one, again, you can work it out, right? You put all particular subspaces in here. So I wrote it here in terms of the matrices. You get this, and you can see that this actually is precisely the action of the Hecke algebra, where we do the flip and we don't do the flip. With factor 1 or q minus 1. Okay, so you can convince yourself that this is indeed the action of the Hecke algebra. Okay, and so now, how are we going to derive our stationary distribution? Well, we need generators for our semigroup, and the generators will turn out to be the lines. Okay, so if we add lines, then so the operator that we had before will now turn out to be add all possible lines and then remove repeated subspaces. And the probability is again xi and then divided by the size of these equivalence classes. Okay, so this is what I just said. The generators are the lines, and then each line, the probability that we assign is given by the support. So we look at the smallest thing in the support. Okay, and then again, you don't need to worry about all the details, but now we can play exactly the same game as we did for the Zettlin library, we look at the right Cayley graph, and we then do this Karnofsky-Rhodes expansion of this right Cayley graph, and then we compute the probability of getting to a particular flag. So if we start here, and let's say we want to get this particular flag where we first add E1, then E1, E3, and then the full space, then well, we get a probability, in this case, y1, so y is just the x divided by the size of the equivalence class. Then we have a loop here, so that's the 1 minus y1, and so on and so on. So you can work out all the probabilities, and that's how you get the formula. And I'm sort of just going to flash the formula for you, but it looks again very similar to before. We have these denominators that you get from the loops, and then we have numerators which are more complicated because we can either flip or we don't flip. So we have sums of x's with q's in there. Okay, and then so what you do is you take this, and then when you lump all the equivalence classes together, so basically you multiply by the size of the equivalence class, that's how you get the stationary distribution for the action on the permutations. Okay, so by lumping, we also get the previous ones that I showed you. And then in the last minute, let me just tell you about eigenvalues. So the eigenvalues for the flag one, again, you get the eigenvalues by looking at subsets, but the multiplicities are now actually not the derangement numbers, but q-deformations of the derangement numbers. And again, this, I guess, corresponds to the fact that sort of these equivalence classes needed to be grouped together. So in this case, a particular eigenvalue occurs now with this q-deformed derangement number. And then the last thing I want to say is we also figured out something about the mixing time. And but this might look a little bit complicated, so let's focus on the picture. So to get the mixing time, one thing I need to say is we have the q, right? That's an extra parameter, but we also have the x's, and now Diaconis actually did the mixing time when he specialized xi to 1 over n. And so we want to do something similar, so we now specialize xi, but to a p deformation of n. So we now introduced another parameter p, right? Because that can be independent. The q from the q-Tsetlin and the x's can have different parameters. So now we have two parameters, a q and a t. So when p and q is 1, we get the Diaconis result, and that's nlogn. But when p is bigger than 1 and q is bigger than 1, we actually get this region here where we have mixing time of order n rather than nlogn. So it actually mixes faster. Okay. Yeah, so I'm basically done, but one thing that I wanted to emphasize is that we don't yet have a direct proof for the action on permutation. So we needed to appeal to this action on the flags. And other things that we are working on is now type C analogs, signed permutations, and also instead of looking at just actions on permutations, you can look at actions on linear extensions of posets. Thank you very much.
Any questions for Alan?
Do you have a coset description of the action or
Yeah.
types? Oh,
You can also write it in terms of cosets. Yeah, I didn't put it on the slide, but if you look at the paper, it's also
Is there any reason you restrict yourself to type A and type C?
No, we are just like working ourselves. Yeah, type C already seems complicated, so. No, but in principle, yeah. One would like to do it for any type.
Yeah, there are a few different actions of the Hecke algebra on words, at least, and I assume also on flags. Have you considered alternate actions, or is there a reason to choose the specific action you did?
So what are the other actions?
So you can, like, I think there are a few automorphisms of the Hecke algebra, which like the action on it changes the action on like the specific basis you chose.
Okay.
But because it's an automorphism, it might be equivalent somehow, but I'm not sure.
Yeah, okay. Perhaps we can talk afterwards. Yeah.
There was one more question here. Any more questions?
Is there any like nice crystal structure on these flags?
Oh. I'm not sure. Like, one second, why would you expect a crystal structure?
I don't know, I was just curious.
You don't have any way to like tweak the Hecke algebra action to get one on any like interesting subvarieties of the flag variety?
Oh. Yeah, again, I'm not sure.
Any more questions? Let's think again.